Okay ma. So next topic is magnetic effects of current ma. Very very interesting topic, very easy topic, and definitely you may get one question is compulsory, and if you are quite lucky you will get 2 questions also, and whatever may be the type of question you will get from this topic. Basics if you are clear, very easily you can solve. Calculation part also ఏమీ ఉండదు, calculation part also 0. Okay, see my magnetic effects of current. See here, first of all, if I take a magnet, listen very very carefully ma, otherwise you cannot understand. North pole, south pole. So we know that magnetic lines of force, they will be traveling from north pole to south pole outside the magnet, and inside the magnet they will be traveling from south pole to north pole. This is how magnetic lines they travel, no? So always magnetic lines, they form loops ma. They cannot travel just like a straight line. For example, if you take a electric charge, positive charge, if you take only positive charge, electric lines always they move perpendicular and outside to the positive charge, no? So always these electric lines, they will be making 90 degrees. And here they never make closed loops. Okay? Unless you place a negative charge, they don't make loops. Clear? But that is not the case in the case of a magnet. So always, magnetic line always forms a loop. Outside the magnet, north pole to south pole. Inside the magnet, south pole to north pole. This is the direction of magnetic line of force. So magnetic line of force is produced by whom? Magnets. Magnetic line of force is produced by magnets only. Clear? So therefore what I say, and I say that magnetic field means a region in which magnet can exert a force, that is called as magnetic field. So magnetic field is produced by whom? It is produced by magnet itself. Are you able to understand? Now there is a scientist called Oersted. I don't know what is his spelling. Ide correct anukuntaru. Clear ma? So there was a scientist called Oersted. He is not a physicist emi kaadu, but he was doing an experiment. Experiment was that he was taking a current carrying conductor. Okay, and he had a magnetic compass. What is a magnetic compass? You know, no? Magnetic compass has a magnetic needle, and whatever the direction you rotate, always it show north pole and south pole. That is called as a magnetic compass, no? Okay, now see my here, if I place magnetic compass here on this line, okay, then it will show direction in the direction of magnetic line of force. Okay ma? It will align parallel to magnetic line of force. Magnetic needle ni meeru ee magnetic field lo pedite ఏ డైరెక్షన్లో అది అలైన్ అవుతుంది? ఇట్ అలైన్స్ ఇట్ సెల్ఫ్ ఇన్ ద డైరెక్షన్ parallel to the magnetic line of force. Same magnetic compass if you place here, again it will align itself in the direction of magnetic line. That's all. If you place magnetic compass here, it will align parallel to magnetic line of force. Okay. Now this person Oersted, he was doing some experiment. Okay, he was taking a current carrying wire, and he had a compass also. Accidentally he placed this current carrying wire parallel to this magnetic compass. Okay, for example, this is a current carrying wire. In this wire current is flowing. Are you able to understand ma? And what is the direction of magnetic compass? This is the direction of magnetic compass. So occasionally, suddenly, without any knowledge, he placed this current carrying wire parallel to this magnetic compass. Okay, so it means that needle is like this. Clear na ma? So this current carrying wire is also like this. So both of them, they are parallel, no? Are you able to understand? So when both of them, they were parallel, he observed that this needle has deflected. Okay ma? Previously needle was like this, no? So there was a small deflection theta. So north pole and south pole, they have deflected like this. Okay ma? This is the biggest shock he had ever in his life. So magnetic needle will deflect in which condition? Only when magnetic field is present. Magnetic needle eppudu deflect avutundi? Magnetic field unnappudu. Is it clear? But when he placed current carrying wire parallel to magnetic compass, it means he placed the wire like this. Okay ma? So this is the wire. So he observed that needle has deflected. Okay? Shocked. Then what he has done, and he went to his home and started doing experiments on this one. Okay ma? Previously he passed 2 amperes of current and placed the wire parallel to the magnetic compass, parallel only. Then he had seen that there is a small deflection 30 degrees produced. Then he increased the strength of current. Okay ma? he increased the strength of current, then he had seen that angle of deflection has also increased. Are you able to understand, ma? Then what he has done, he has taken the same magnetic compass, clear, ma? And he made the current to pass in opposite direction. Then he has seen that the needle deflection also has changed the direction. Previously needle was deflecting like this, no? Now he observed needle has deflected like this, in opposite direction. Okay? It means that by this he came to a conclusion that, and he has done one more experiment also. So this is the magnetic needle, okay, ma? And he placed the current carrying wire perpendicular to the compass. Okay? In this condition, there is no deflection. He did not see any kind of deflection. Are you able to understand? So deflection was shown in which condition? Only when current carrying wire was parallel to magnetic compass. Are you able to understand? And when he increased the strength of the current, deflection also increased. When he changed the direction of current, the direction of deflection also has changed. So therefore he came to a conclusion that current carrying conductors also, they will produce magnetic field. Okay, ma? So until this experiment was done until I think in 1807 or around this time. I don't remember the exact date. Around this time he has done this experiment. So until this time, electric field was separate. Magnetic field was separate. Electric field is produced by electric charges. Magnetic field is produced by magnet. Okay? But first time he observed that electric charges are producing magnetic field. That was the observation done by Oersted. Are you able to understand? So make a note of it. So therefore what we write, okay, ma? When he placed, he means Oersted, ma? When he placed current carrying conductor parallel to magnetic compass, okay, ma? Then he observed some deflection in the needle. Which needle? Magnetic compass. Okay, ma? This proves, and further experiments many are there, ma? I am writing all this, only concept I am writing. This proves that any current carrying conductor okay, ma, produces magnetic field. Okay? Any current carrying conductor always produces magnetic field. Okay? So this was the biggest observation in the history of electromagnetism. Only because of this observation only we have fans today, we have generators, we have motors. Every observation was based on his observation. Okay, ma? Every electrical apparatus based on the observations of Oersted. Otherwise there is no fan, there is no AC, there is no refrigerator, nothing. Okay? Now see. So therefore further experiments were done and it was proved that magnetic lines are arranged like closed loops around the current carrying conductor. CCC. You write in full form. CCC means what? Current carrying conductor. Okay? So for example, this is the current carrying conductor. Then magnetic lines of force were arranged like this. Are you able to understand? Bangle ivra okkasari. Sima. So what is the arrangement of magnetic lines of force? Let us see. It is like closed loops around the current carrying conductor. It means if this is the current carrying conductor, in this conductor current is passing, magnetic lines of force, it is arranged like this. This is the arrangement. And the center of this magnetic loop is the wire itself. Okay, ma? So this is behaving like an axis and magnetic lines are formed like this. So if you increase the strength of the current, many magnetic lines will develop. Smaller bangle, big bangle, another big bangle, like this. Are you able to understand? That is the arrangement of magnetic lines of force. Okay? So make a note up to here. So there are closed loops. Small loop, bigger loop, and another bigger loop. Okay, ma? Next, see. Now the question is, what about the direction of these magnetic lines of force? See, magnetic lines of force always has a particular orientation. No? See the orientation? See, for example, this is a magnet, north pole and south pole. So always they travel from north pole to south pole outside the magnet, and inside the magnet they travel from south pole to north pole. 1 minute. See ma'am. So magnetic lines always has a particular orientation. This is the direction. No? Huh? So therefore these magnetic lines also, they should have a direction. Okay. So direction should be either in this direction, or direction should be either in this direction. Which direction? That is very important. So therefore next we study about orientation of magnetic loops. Okay ma? This direction of orientation is given by right hand grip rule. Right hand grip rule. Okay ma? If you don't understand this rule, you better don't study this topic. So that is the importance of this rule. Okay ma? So orientation of magnetic loops is given by which rule ma? It is given by right hand grip rule. Okay? So right hand grip rule. Let us study the full form of this rule. So hold the current carrying conductor. అంటే దిస్ ఇస్ థియరిటికల్ మా. పట్టుకోమని చెప్పినారు, నిజంగానే పట్టుకున్నారంటే పోతారు పైకి మీరు. థియరిటికల్. హోల్డ్ ద కరెంట్ క్యారీయింగ్ కండక్టర్ with right hand such that thumb is in the direction of current. Thumb is in the direction of current. Okay ma? Then curling of fingers gives the direction of magnetic lines of force. So this rule is called as right hand grip rule. Okay? Now let us see what is the meaning of this rule. Okay ma? See. So see ma, this is a current carrying conductor, and this is the magnetic loop which is present around this conductor. Okay ma? So how to find out its orientation? It can have two orientations no ma? Either it can have this orientation, or either it will have orientation in opposite direction. Which one is correct? Which rule we are discussing about? Right hand grip rule. So hold the conductor with your right hand such that thumb is in the direction of current. Thumb should be in which direction? Thumb should be in the direction of current. Current is in this direction, no? So hold it like this. Clear? When you hold it, now you are curling your fingers in this direction, no? In this direction. So you can curl your hand outside the board also. You can curl your hand inside the board also. Outside the board, from where I am curling from top to bottom. This is the current carrying conductor. Clear? So I am holding like this. This is the current direction. Thumb direction also should be same. So I am curling like this. So this curling is out of the board, no? Curling lopalkunda baitukunda. Out of the board. So from top to bottom. That is my orientation. Clear, no? So same magnetic line of force I will draw like this. Clear ma? So this is a thick line. This is a dotted line. What does the thick line indicate? Outside the board. Dotted line indicates magnetic loop which is present inside the board. Clear no ma? So in outside the board I am curling from which direction to which direction? Top to bottom. And this is the magnetic line which is present out of the board, no? So this is my direction of magnetic line of force. That's all very simple. Okay ma? So outside the board it is from top to bottom. So automatically inside the board it is from bottom to top. This is my direction. Are you able to understand ma? So orientation of magnetic line of force, if you don't understand, you cannot do a single problem. Oka problem kuda manam cheyalem. Is it clear? Very simple. So hold the conductor with your right hand such that thumb is in the direction of current. Curling of fingers will give the direction of magnetic lines of force. That's all. Clear nama? For example, consider this is a current carrying conductor. Current is flowing in this direction. Now can you draw the orientation of magnetic line? ఇట్ట గీసినామని చెప్పి లెఫ్ట్ హ్యాండ్తో పట్టుకుంటారు మీరు, రైట్ హ్యాండ్తోనే పట్టుకోవాలా. కమాన్ Try to draw the direction. Orientation draw చేయాలి, అవుట్ సైడ్ ఇన్ సైడ్ కాదు. సో ఫస్ట్ యూ డ్రా ఏ థిక్ లైన్, యూ డ్రా ఏ డాటెడ్ లైన్. క్లియర్ నమ్మా? సో థిక్ లైన్ ఇండికేట్స్ మ్యాగ్నెటిక్ లైన్ అవుట్ ఆఫ్ ద బోర్డ్, dotted line indicates magnetic line inside the board. So how you can curl your fingers? Tagada Subara ittabote thumb is in opposite direction to the direction of current. Thumb should be in which direction? In the direction of current. So how can you hold it? You have to hold in this direction. Huh? Now you are curling inside the board or outside the board? Inside the board. And inside the board you are curling from top to bottom or bottom to top? Top to bottom. So that's all. This is my direction. Clear no? This is the direction of magnetic line of force. Understood nama? So direction of magnetic line is very, very important. Arthamavutunda kadra? Very simple. Clear? Now see. So after studying right hand grip rule, now we study about the importance of B dash. What is B dash? Magnetic field strength. Okay ma? Or you can call it as just magnetic field also, or you can call it as magnetic flux density also. There are many names to this one. Okay, ma? So next concept we are discussing about what? We are discussing about magnetic field strength. Okay? See, in electric field we studied E dash, no? Electric field E dash chadivunam kada. What is E dash? Electric field strength or electric flux density, which is represented as force experienced per unit test charge. Clear no? Same concept in magnetic field. Force experienced per unit south pole or per unit north pole is called as magnetic field. Okay ma? So in electrostatics we represent by E dash. In magnetic field we represent by B dash. Clear? If E dash is greater, then at that point force is greater, no? Similarly, if B dash is greater, at that point also force will be greater. That's all. Clear? Now see. So therefore what does B dash indicate? It indicates strength and direction of magnetic field. Okay ma? So it indicates the strength and the direction of magnetic field. So it is a tangent to magnetic line of force. It is a tangent to magnetic line of force. E dash also same nama. For example, if you consider this is positive charge, if you consider this is negative charge, electric lines will travel like this, no? Clear? So here if I want to calculate the direction of E dash, how can I calculate? Electric field direction kavalante em chestamu? Direction. Electric field direction, right? We draw a tangent. Okay ma? And this tangent will give the direction of E1 dash, electric field at this position. Similarly here if you want to calculate the direction of electric field, here you draw a tangent. Tangent will give the direction of electric field at second point. Same concept with magnetic field also. Okay ma? For example, if I take a magnet, okay, so this is a magnet, north pole and south pole. So this is the direction of magnetic line of force. Clear nama? So this is the direction of magnetic lines of force. Okay? Sima, for example, this is point A and this is point B. At these 2 points, I want to find out the strength and direction of magnetic field. How can I calculate? So at point A and point B, I want to calculate B dash, magnitude also, direction also. How can I calculate? First of all, where magnetic field will be greater? At A or at B? Huh? Yeah, why? Here magnetic lines are very closely associated, no ma? If magnetic lines are more in number, automatically strength will be greater. And here magnetic lines will be very less. So here strength of magnetic field will be very less. Then what about direction? Tangent to magnetic line. So therefore here if I draw a tangent, this should be the direction of tangent, no? So this is BA dash. Clear? Magnetic field at point A. Direction ఎలా వచ్చిందో అర్థమవుతుంది కదా? Just to magnetic line we have to draw a tangent. Is it clear? Now here if I want to find out the direction of magnetic field at point B, so I will represent by a very small vector. So B dash. See here length of the vector is very large. Vector length చాలా పెద్దగా ఉంది చూడండి. Here length of the vector is very small. Why? Strength is very less. Okay, ma? So in lower classes you should have studied, no, ma? Near the poles, strength of the magnet is very large. Chadinara ee point? 10th pass ayinaru kada. Yeah. So near the poles, strength of the magnet is very large. So at remaining points, the strength of the magnet is very less. Are you able to understand? So therefore, same point we are discussing here also. So therefore, I can say magnitude of BA dash is greater than magnitude of BB dash. Is it clear, no? So magnetic field B dash represents what? It just represents the strength and the direction of magnetic field. Is it clear? Okay, write down up to here. See, ma. So now we have understood what is meant by B dash, no? Now see, ma. Now to this current carrying conductor, let us see what are the different directions of magnetic fields at different points. See, ma. So this is a current carrying conductor, okay, and this is a magnetic line. Okay, direction you have understood, no, ma? So this is the current carrying conductor, this is the direction of magnetic field. Okay, itla round ga draw cheyalem kada, andukani itla chestha unna. Meer endo anukuntaru malli. Now see, now can you say what is its orientation? So top to bottom. Outside the board it is from top to bottom. Inside the board it is from bottom to top. So closed loop. Are you able to understand, ma? Now I am taking 4 points, ma. So at these 4 points you should say the direction of B dash. Clear? So point number 1, point number 2, point number 3, point number 4. At these 4 points you try to say what is the direction of B dash. This is magnetic line only, no? Magnet creates magnetic line. Current carrying conductor also produces magnetic line. So this is also a closed loop. Now to this closed loop at 4 points, find the direction of B dash. Find direction of B dash. B dash direction find out chain. Come on. See, ma. So let us see the directions of B dash. See, ma, let us take the first point. Okay. Now this is the current carrying conductor. Current is flowing in this direction, and this is the bangle. Bangle in the sense magnetic loop which is formed. So now in this magnetic loop, in this magnetic loop, where is point number 1? In the topmost position. No? Clear, no? Here at the topmost position, point number 1 is present. Okay. Now here at this point, how magnetic line is moving, ma? So at this topmost position, either it should enter the board or either it is coming out of the board. Is it coming out of the board or into the board? Coming out, no? Which rule? Right hand grip rule. This is the direction of current, no? And this is my right hand only, no doubt. So therefore, I curl my hand like this. This is the direction of current. Magnetic line is coming out of the board. So here at topmost position, I have to draw a tangent. Okay? So how can I draw a tangent? This is the topmost position, no? Coming out of the board. Here you draw a tangent. This is my tangent. Are you able to understand, no? This is my tangent, no? This is the direction of magnetic line, and this is how I have drawn a tangent. This is the direction of tangent. So this tangent, is it coming out of the board or inside the board? Out of the board. That is my direction of magnetic field at first point. Are you able to understand, ma? So at point 1, what is the direction of B dash? B dash is perpendicular and out of board. Okay, ma? B dash is perpendicular and it is coming out of the board. Okay. Now can you say point number 2? Where is point number 2? Exactly at the bottom of this magnetic line, no? Here. Now here magnetic line is entering into the board or coming out of the board? Entering into the board, no? So therefore how I have to draw a tangent? I have to draw a tangent like this. This is my tangent, no? Okay, ma? So this is entering into the board and perpendicular to the board. This is the direction of tangent, no, ma? Clear? So this is coming out, this is entering inside. So therefore, those directions we cannot draw because గాల్లో ఇట్లా లైన్ డ్రా చేయాలంటే కష్టం అనమాట. ఓకే, అట్లా లోపలికి డ్రా చేయాలన్నా కూడా కష్టం. సో therefore what I write, B dash is perpendicular and inside the board. At which point? At point number 2. Okay. Point number 3. Line, magnetic loop. Where is point number 3? In this magnetic loop, where is point number 3? ఇక్కడ ఉంది point number 3. Here is point number 3. Okay, ma? Point number 1, point number 2, point number 3, point number 4. Here point number 3 is present. So here magnetic line is coming down or moving upwards. First of all, is it out of the board or inside the board? Out of the board. So here magnetic line is going downwards. It means here at this point I have to draw a tangent, and this is the direction of tangent, downwards. Clear, no? Magnetic line is going like, this is the orientation, no? Top to bottom. So tangent also top to bottom. Clear? Here I can draw, because it is in this direction. This is the direction of B dash. Okay? So B dash is in the plane of board. B dash is in which direction, ma? In the plane of board, and it is downwards. Okay? So downwards. Now what about point number 4? Where is point number 4? Behind this angle, no? Back of the board. And it is moving from bottom to top. Bottom to top. So therefore, this is point number 4, and this is how I have to draw a tangent. This is my direction of tangent. So therefore, here what is, here also I can draw. This is the direction of B dash. Clear, no? So B dash is in the plane of board. B dash is in the plane of board and upwards. Understood, Amma? How to find out the directions of B dash? Is it clear? That's it. Okay. So remember, up to here, we will continue in the next class. Okay. Student. So next we are discussing about force experienced by moving charge in an external magnetic field. Okay, ma? See, yesterday what we studied that if this is a current carrying conductor, this current carrying conductor produces magnetic field. This is what we studied, no, ma? Current carrying conductor always produces magnetic field. Okay. So what we studied, ma? We studied that current carrying conductor produces magnetic field, no? Clear? So current carrying conductor means they are basically charges only, no? What is meant by current? Flow of charge. Clear, no? So therefore, we say that if current is flowing, magnetic field is produced. It means if a charge is flowing, then also field is produced. That is the meaning of this one, no? Are you able to understand? So therefore, what we say that any moving charge produces magnetic field. Any charge, whether it is a positive charge or negative charge, if it is moving, definitely it produces magnetic field. So this charge, if I place in another field, another external magnetic field, then what happens? These two fields, they will interact with each other, no? And that interaction will result some exertion of a force on this charge. This is what happens. Are you able to understand? So let us write the statement of it. So moving charge produces magnetic field. So if this charge is placed in another external field. External field means which field? External magnetic field. Okay, ma? Then these two fields interact with each other. And charge experiences a force. Charge experiences a force. Clear? Now let us see this force experienced is in which direction and what is the magnitude of this charge. Okay? Now see. Consider this is external magnetic field, ma. This is B dash. What is B dash? External magnetic field. Clear, no? And this is the charge which is moving. Plus Q charge moving with the velocity of V. What is V? V is called velocity. Okay, ma? And the angle between this magnetic field and the direction of this charge is theta. So what is theta here? Theta is the angle between external magnetic field and velocity of charge. Clear, no? Then charge will experience a force which is called Fm. And what is this Fm? This is called magnetic Lorentz force. What is the name of this force, ma? Magnetic Lorentz force. Clear? And this magnetic Lorentz force magnitude is QVB sine theta. So this is the equation to calculate magnetic Lorentz force. Clear, no? And what is this magnetic Lorentz force? Force experienced by the moving charge when it is placed in external magnetic field. Clear, no? So Q is magnitude of charge which is moving, V is the velocity, B is the strength of magnetic field, and theta is the angle between magnetic field and velocity. Are you able to understand, ma? So one point which I can understand is magnetic field is directly proportional to charge, directly proportional to, force experienced is directly proportional to velocity, magnetic field, and angle theta also. Clear? Not exactly angle theta, proportional to sine theta. So you can write here. So Fm is directly proportional to Q, Fm is directly proportional to V, Fm is directly proportional to B, Fm is directly proportional to sine theta. So these are the factors on which magnetic Lorentz force depends upon. Okay, ma? Now the question is, what is the direction of force? Force is a vector quantity, no, ma? Force is what kind of quantity? Vector quantity. So therefore definitely this force should have a direction also, no? And that direction is given by direction of magnetic Lorentz force. It is given by Fleming's left hand rule. Fleming's left hand rule. Okay, ma? So what is Fleming's left hand rule? Let us see. Clear? See. So this is the direction of B dash. Consider this is the direction of, or consider this is the direction in which charge is moving, Q charge moving with the velocity of V. Okay, ma? And we are discussing about only positive charge, ma. If I take a negative charge, the direction will be exactly reversed. Clear? We are discussing only about positive charge. Then here, how to find out Fleming's left hand rule? So stretch the 3 fingers of your left hand like this. Clear? So forefinger is there, no? Forefinger indicates the direction of magnetic field. Clear? And this middle finger is there, no? Middle finger indicates the direction of motion of charge. Then thumb gives the direction of force experienced by this charge. Are you able to understand? Now can you say this charge is experiencing force in which direction? Chappandi. Aika. Alochin chappandi. Out of the board. Sima. This is how I place this left hand, no? This is the direction of B dash. This is the direction of charge. Then thumb is perpendicular and out of the board. That is how we use the Fleming's left hand rule. Clear, no, ma? So therefore, forefinger indicates what? B dash. Middle finger, direction of charge. Clear, no, ma? Thumb gives what? Thumb gives direction of Fm. Fm means magnetic Lorentz force. Clear? Make a note point. Note point is that if charge is negative, then exactly opposite direction of force. Then you have to apply force exactly in opposite direction. Clear? So here force is in which direction? So here force is perpendicular to B dash and Q, or we say V dash, velocity. Okay, ma? Perpendicular and out of board. This is the direction of force. Are you able to understand? See, ma, this force experienced by this charge, it will be perpendicular to both the vectors. It will be perpendicular to B dash also. It will be perpendicular to velocity also. Okay, this is one important point. So around this charge also magnetic field will be there, no? So this magnetic field interacts with this field, and it will experience a force according to Fleming's left hand rule. That's it. Okay, right. And here one point which I can understand is, see, ma, for example, if this is the direction of B dash and charge is moving in this direction with a velocity of V, now can you say it will experience how much magnetic Lorentz force? Can you say? So this is a charge of plus Q, 0. How can you say it is 0? Sin theta is 0, no? See, ma, here Angle is how much? Angle between B dash and V dash is 0. Clear, no? So it means charge is moving in the direction of magnetic field. So therefore, sine 0 is 0. So therefore, magnetic Lorentz force formula, QVB sine 0, it is also 0. Okay. Similarly, for example, if this is the direction of B dash and charge is moving in opposite direction. Now can you see? ఆలోచించి చెప్పాలి. So here theta is how much? 180 degrees. Sine 180? Sine 180 minus 1. Sine 180 is 0. Clear, Nama? So therefore here also magnetic Lorentz force is how much? Here also it is 0. Are you able to understand, ma? So if a charge moves in the direction of B dash or in exactly opposite direction to the direction of B dash, in both conditions it will not experience any force. This is a very, very important point. Clear, Nama? So the parallel ga vellina, anti-parallel ga vellina sare, it doesn't experience any force. Clear? So better make a note of that point. So what is the note point I can write? So if charge moves parallel to B dash or anti-parallel to B dash, magnetic Lorentz force will become how much, ma? It is 0. Clear? One more case I will write down, see, ma. So this is the direction of B dash. Okay. So at a distance of 10 centimeter. No, this is not correct. Consider this is B dash. This is the direction of B dash, ma. So here there is a charge Q plus 10 microcoulombs of charge. Strength of magnetic field is, let it be 10 Tesla. Okay. Now can you say what is the magnetic Lorentz force experienced by this charge? Huh? Anta? 0. Sure. Endukala? Charge is present here. Huh? Theta em ivalledu vaadu. Charge is here. Charge is plus 10 microcoulombs and magnetic field is 10.
Positive charge magnetic field direction experience chestundi.
Brilliant. Anybody? Force is 0. At least say the reason why force is 0. Yesu Prabhu vilani kaapadandi. Q V B sin theta. Velocity ekkada undi daniki? Q into velocity is 0, magnetic field is there, and angle theta we don't know. So totally it is 0. It is in rest position. No, if it is in rest position, it does not experience any force.
Last answer sir.
Abba, నేను రాసిన తర్వాత. So therefore another important point is what, ma? If a charge is in rest position, it does not experience any force. It does not experience any force. What is the reason? If it is in rest position, it doesn't produce any magnetic field. Clear, no? Charge rest lo unte magnetic field produce avadu. Clear, no? Then there is no question of force experienced. So these are the points which you should remember.